Good morning. Today, welcome to another video. Today, we are going to discuss about small signal operation. So, before starting of the small signal operation, let us find out what is the meaning of the small signal modeling or small signal operation. Basically, it is a common analysis technique. Basically, in this technique, we used to approximate the behavior of electronic circuits containing nonlinear devices such as diodes, transistors. So, as we are going to discuss about a MOSFET, and you know that this MOSFET or if field effect transistor is a non-linear device. So here, basically, we are providing a DC voltage for biasing, and along with that, if you can provide a small AC signal, and we can check what is the behavior of this uh, MOSFET for this AC signal, this small signal, and the small signal is something which is very small to the DC voltage. So that's called that if I am providing a small signal to the MOSFET and checking what is the how the MOSFET behaves, that is called small signal modeling or small signal analysis. So here basically by using the small signal analysis, a nonlinear circuit is approximated to a linear circuit. Okay, so you can see in this diagram. In this diagram, we have taken a N channel MOSFET. You can see here I have taken a N channel MOSFET. We have a gate here. We have a drain here, and we have a source here. And gate to source voltage we named as VGS. You can see V0. I'm using as a DC voltage. Along with that, I'm using another term. It is called a V mic. So V mic is providing a small signal, which is a sinusoidal signal. We can say that is V equal to Vm sin omega t. Okay, so this Vm sin omega t, and this Vm, the maximum value of the signal is very small than the V0. Along with that, at the drain side, we are providing a voltage of V1. You can see voltage of V1 here. As I told before that the input signal is of small in magnitude. So the input signal is of small in magnitude. That means your Vm is very less than V0. So from uh, this thing we can sure that the VGS, here I'm getting VGS is nothing but the V0 plus V mic, or you can say that V0 plus Vm sin omega t. Okay, so if I apply KVL, we can get VGS equal to V0 plus Vm sin omega t. If we want to find out the drain current, and we know that for any amplification, the MOSFET should operate in the saturation region. So the equation for the saturation region, as you know that ID equal to 1 by 2 mu n COX W by L VGS minus VTH square. Now, whatever VGS I got here, I'll replace this VGS. I'll replace this VGS here. So instead of VGS, I wrote here Vm sin omega t plus V0 minus VTH square. Now, if I'll take this V0 minus VTH as a common, I'll get V0 minus VTH common. So I'll get here 1 plus Vm sin omega t V0 minus VTH whole square. So all I kept, and I kept a square. Now I want to bring this V0 minus VTH so out of this square bracket. So when I will take it out, I will get V0 minus VTH whole square, and whatever left 1 plus Vm sin omega t V0 minus VTH whole square. Let mark this thing as equation number 1. So I got here ID equal to, I got here ID equal to 1 by 2 mu n COX W by L V0 minus VTH square plus 1 plus Vm sin omega t divided by V0 minus VTH whole square. So they told that already we know that this VGS minus VTH is nothing but called VOV or override voltage. Okay, so this and already we already told that this Vm is very less than V0, so I can say that this Vm is very less than V0 minus VTH. So if Vm is very less than VTH, then this Vm sin omega t divided by V0 th whole square is also very less than 0. So this value is also very less than 0. That means if I'll take if I'll if I want to just hold for a minute. If I want to find out 1 plus x whole square, if I want to find out 1 plus x whole square, I'll get 1 plus x square plus 2x, and x is very less, so that this x square we can neglect it with respect to 2x and 1. That's why 1 plus x square I wrote as 1 plus 2x. If I will take the similar case here, if I will take the similar case here, 1 plus Vm sin omega t divided by V0 minus Vth whole square, and this value is very less than 0, so that we can neglect the square of the particular value. So in this way, so this one I got like this. So 1 plus 2 into Vm sin omega t divided by V0 minus Vth. Okay. So now our drain current, it came like that, 1 by 2 mu n cu x w by L V0 minus Vth whole square into 1 plus 2 into Vm sin omega t divided by V0 minus Vth. Okay. So from the beginning of the class, I told that this Vm sin omega t is very small than the V0. That means we can approximate that this VGS is equal to V0. So as this V mic or Vm sin omega t is very small, so we can approximate here that V0 is equal to VGS. Now by putting this V0 equal to VGS, I'll get the drain current becomes ID equal to 1 by 2 mu n cu x W by L VGS minus VTS square plus this thing. And we know that this 1 by 2 mu n cu x W by L VGS minus VTH whole square. So this one is nothing but the drain current due to bias, due to the V0. So I'll name as this is called ID0, and the current quantity given by the battery or given by the DC source. Now if I'll write down, instead of this, if I'll write down ID0 here, so my drain current equation becomes this: ID equal to ID0 into 1 plus 2 into Vm sin omega t divided by VGS minus VTH. Then I just expanded that equation. So ID0 will go inside and multiplied with each term. So now you can see this 2 into ID0 Vm sin omega t divided by VGS minus VTH is called the current due to the signal, due to the V mic or Vm sin omega t. So due to this Vm sin omega t, I got a current that is called signal current. Okay. Now if I can as this MOSFET is a voltage control device. Now uh, if this is our MOSFET, N channel MOSFET, and in this N channel we have a DC bias as well as a small signal, and due to that I'm getting a drain current ID here. So this drain current is due to the two currents. One is due to the ID0 bias current, and due to the 2 into ID0 Vm sin omega t divided by VGS minus VT is equal to signal current. So the ID, the drain current, it consists of two components. So if I will decompose it, I will get like this. So I have taken here only the DC bias or battery, so I will get ID0 here. Next, when I will take the V mic or signal only, for that I am getting 2 into ID0 Vm sin omega t divided by VGS minus VTH. So this is your bias current and this is your signal current. This is your signal current. This is your signal current. Now I want to write down in this format. So you can see here, this is your gate, this terminal is your gate, this terminal is your source, this terminal is your drain. Okay. So now that VGS, so the voltage across gate to source equal to VGS, which is nothing but V0 plus V mic, and to this drain current, to this drain, I'm getting two voltages. Two currents are coming. Just hold for a minute. So two currents are coming. Okay. So this is ID0 or bias current, and this is 2 ID0 into Vm sin omega t divided by Vgs minus Vt. So it is I called signal current here. Okay. So now if you remember, this 2 into ID0 divided by Vgs minus Vt, this is called Gm, or is it called transconductance. This is called transconductance. Already we know. Okay. So here I am finding a current ID, which is the algebraic sum of two currents. One is bias current and another is signal current. ID0 and 2ID0 divided by Vgs minus Vt and Vm sin omega t. So this thing I wrote as Gm. So now my current, the signal current, becomes Gm into Vm sin omega t. Gm into Vm sin omega t. Or I can write down here Gm into V mic. So mic is the input signal. Okay. Now again I will decompose the same circuit. I will decompose the same circuit here. You can see here I got a model due to the bias current where input is V0 and the current is only ID0, and for the small signal I am providing the input as V mic or only the sinusoidal signal, and I am getting the current which is nothing but Gm into V mic. So I can decompose the above circuit into two circuits. So now we are interested in this circuit. So we are interested in the small signal model. So in the small signal model, you can see here from the circuit you can clearly see now in this case the VGS here is nothing but the V mic. The VGS is nothing but the V mic. So here the current ID, so the current ID or the current which is flowing due to the small signal is nothing but the multiplication of transconductors as well as the voltage. That's why the small signal model basically regards only change in voltage and change in current. So this change in voltage you can name as del of VGS. If the at the input side the change in voltage is del VGS, so the current which is flowing through the drain is called GM into multiplied with the del VGS. This is basically the current due to the signal. The current due to the signal. Which signal? The small signal. So current due to the small signal. Okay. So now this I want to draw a small signal of this particular circuit. Okay. So you can see here this is your bias voltage. This is your signal. I have a gate here. I have a source here, and we have a drain here. And to the drain resistance is connected as RD, and to the source resistance is connected RS, and we have a input side voltage is V1. If we want to draw its small signal, then I will have to draw like this. So first I will take this is the gate here, then source. So in between gate to source, let the voltage is V1, not this V1. So this is not this V1. Let's hold it. So don't confuse it. Just let me change the name here. This is your V in. Wait. V1. Okay. So this is another. Let me take this is your V. Name I will change it. V1. Let this is your, sorry, I want to write like this. Let this is the symbol is different. Let this is your V1. So I write V1. So whatever is the voltage difference between gate and source, let this is your V1 and RS. This is your source terminal. This is your drain terminal. This is your gate terminal, and the current is whatever the current source or current is flowing. This is nothing but the multiplication of transconductance and the voltage difference between gate to source. Gm into V1 and the RD and RS we kept as it is at the source as well as at the drain. So when we are considering the small signal model at that time, so basically the voltage source will be short circuited. The voltage source will be short circuited. Remember this thing. This is very, very important. The voltage source will be short circuited and current source will be open circuited. The current source will be open circuited. So now this V1, whatever be the V1 is there and whatever be the V0 is there, both will be short circuited. So only we have a signal here V in. We have an input signal here V in. Okay, we have input signal here V in. So now whatever with the voltage across gate to source, that will be multiplied with the transconductance to get the drain current. Okay. Now will come, is there any effect of channel length modulation on the small signal? If for the channel length modulation has an effect on the small signal analysis or not? Okay. So now here I have taken a N channel MOSFET where this is your source, this is your gate, and this is your drain. And I have taken there is a constant DC voltage source, constant voltage source, and due to that, if there is a change in voltage, if the change in drain to source voltage, let VDS is changed to VDS plus del V. For that, I am getting a change in current also, ID into del ID. So now if we write down the current equation for the channel length modulation, you can see ID plus del ID, we know that 1 by 2 mu n COX W by L VGS minus VTH. Previously we have 1 plus lambda into VDS. So now the VDS becomes VDS plus del B. So lambda is multiplied with both. So lambda is the channel length channel length modulation coefficient. Okay. So after small mathematical simplification, so I multiplied like this 1 by 2 mu n COX W by L VGS minus VTH square is multiplied with 1 here and 1 into VDS first, then lam, lambda into del V second. So when I multiply with this term, this is nothing but your drain current. So I wrote here ID. Then 1 by 2 mu n COX W by L by into VGS minus VTH square is multiplied with the second term lambda into del V. So I wrote here. Okay. So in the left hand side ID is there. The right hand side also I got ID. So ID will be cancels out. So I got here del ID equal to this much. Now if I'll find out what is del V by del ID. So del V by del ID. So I got this is 1 by lambda ID, which is nothing but the R0. So R0 is nothing but the output resistance. Okay. So due to this channel length modulation, we are getting the resistance R0 output resistance, which is nothing but 1 by lambda. Sorry. Why I get 1 by lambda ID? Correct. VD del V by del D. So I'll get 1 by lambda, not ID. Mhm. Okay, lambda into ID, sorry. Just little confusion here. So lambda into ID I will get. So this whole term 1 by 2, the whole term here 1 by 2 mu x. So this thing is nothing but the ID. So into lambda, so I will get. So I got like this output resistance, nothing but your R0. So now this output resistance will be connected parallelly to the current source. Okay, so the output resistance is connected parallelly to the current source. So now, so if I want to draw its small signal analysis by considering the channel length modulation, only we need to connect a resistance, output resistance parallel to the current source. Now, I have taken a small signal model for the PMOS device as well as small signal device for a NMOS device. So you can see from the symbol that this is your NMOS, the arrow is outwards, this is NMOS. So between gate to source, let the voltage is V1 and the current is flowing from the drain to source. The current is GM multiplied by the V1 and a R0 is connected parallel to this. Okay. If I want to draw the small signal model for the PMOS, as you can see here, the arrow is inwards and that is the source. So for that, the diagram remains same, only the direction is changed, or you can say that it is flipped. So this is your source, this is your gate. So this is your gate to source voltage. I have taken V1. You can see the arrow was just flipped. So this is your GM into V1 and this is your R0. Nothing changed, only this is flipped. This is your small signal model for the PMOS. Okay, this is a small signal model for the PMOS. Now, if we know that the small signal model for both NMOS and PMOS, then we can able to draw the small signal analysis for the CMOS, because the complementary MOSFET is the combination of NMOS and PMOS. Already you know in the digital logic design, when you are designing the uh, different circuits using CMOS. So basically we have a NMOS on the PMOS on the top and we have a NMOS at the bottom. Okay, same thing we are doing here. So, so I have taken a circuit where we have a NMOS. So this is your gate, this is your source, this is your drain. Similarly for the PMOS, this is your source, this is the gate, and this is the drain. So both drains are connected together. Now here both gates are connected together to form a common gate, and here we are supplying a DC voltage of V0 and a small signal of V in. Okay, so NMOS basically it is connected to ground, and this source of this PMOS connected to the supply V1. Now if I want to draw its small signal model, so we need to consider these two diagrams. We need to remember these two diagrams, NMOS and for NMOS and for PMOS. Okay, so now so I whatever the voltage sources are there, like the DC voltage sources V0 and V1, this will be short circuited. So only signal left. So this is your V in. I have taken here. This is your V in. Okay, and in between, let in between gate to source, the voltage is V1 for the NMOS. So in the down, I am considering NMOS. So as the gate to source voltage is V1, so I am getting a current between drain to source is GM1 into V1, GM1 into V1, but where the GM1 is the transconductance for the MOSFET M1. Okay, so this is your GM1, and parallel to that I have connected a output resistance of R0. So you can see, so this is the drain for the NMOS. Okay, so this is the drain for the NMOS. So if you can think that, so this entire is the NMOS. It's green color is the NMOS. Now the same I want to design for the PMOS. I want to design for the PMOS. So you can see here for PMOS we have a gate here, source here, and the voltage difference between gate to source is V2. Gate to source is V2, and whatever the drain current is flowing from drain to source. So this is your drain basically. So drain to source current is flowing GM2 into V2, GM2 into V2, and parallel to that the output resistance is R02. Okay, and so I can see that. So in this blue color, this is your PMOS. Okay, both drains are connected together, and you can see as V1 is there short circuited. So the source of the PMOS and source of the PMOS is connected here. Source of the PMOS and source of the NMOS is connected here. So this is they are connected like this. So this is the small signal modeling for the CMOS. This is the small signal modeling for the CMOS. So if you have any doubt, you can ask me in the comment section. Let's practice all these things. Small signal model for the CMOS, small signal model for the PMOS, and how we are getting what is the effect of this channel length modulation on small signal, and how we are getting all these signals